Hello, this is 637. I'm Charles Bouman, and we're going to finish up the stuff on eigenimage and eigensignal analysis. So we were right at the very end last time when I just ran out of a little bit of time. So let me see how I'm going to do this. So, okay, let me just do a quick recap, maybe, of where we were. So you remember. Let me see. Hold on. Okay. So if you remember, the idea is, well, first we have an SVD. So an SVD is something that can be applied to a non-symmetric matrix. Eigenvalue decomposition. Let me just make a quick comment here. For eigenvectors, eigen decomposition, you see, the problem is that for when A equals A transpose, okay? If A is a symmetric matrix, then you have A equals E transpose lambda E, okay? Hold on, I got that backwards. I put the transpose in the wrong place, okay? So the eigen decomposition of A is E lambda E transpose, where this is diagonal, and lambda and E are both real. Okay? So if A is a symmetric matrix, a real symmetric matrix, so this is also real. So if A is a real symmetric matrix, then its eigen decomposition has this structure, right? It's the and lambda here is diagonal, E is orthonormal. Normal. Okay? Which is to say that E transpose, or E transpose E equals I, either way, but I think it's more intuitive to think of E transpose. So when A is symmetric, the eigen decomposition has all these nice properties. First of all, the eigen decomposition diagonalizes A. So if I take E transpose A times E, that's lambda. So the eigen decomposition diagonalizes the matrix when it's symmetric. The eigen decomposition is real, and the eigen decomposition is orthonormal, okay? Now, when A is not symmetric, a lot of these things are not true. When A is not symmetric, there's a concept of eigenvectors and eigenvalues, but it gets all kind of messy, frankly, okay? What'll end up happening is if A is not symmetric, then you have A times E equals lambda E. That's the eigenvalue equation, right? And so there'll be eigenvalues and eigenvectors. But first of all, now if the eigenvalues are unique, okay, then each eigenvalue will correspond to a distinct eigenvector. And it is possible to diagonalize a matrix, but if A is not symmetric, then first of all, the E's will be complex, the lambdas will be complex, and then also what will happen is that the E's won't be well, they can always be normalized, but they won't be orthogonal, okay? So, and in general, the lambdas may not be unique, in which case, if you have duplicity, duplicity, no, that's not the right word, forget that. If you have multiplicity in the eigenvalues, okay, then what can happen is all kinds of nasty, weird things can happen, okay? So, if you have multiple eigenvalues, it might be that the multiple eigenvalues correspond to a subspace which is spanned by a set of eigenvalues. So in that case, the eigenvectors are like non-unique, okay? Or it could be then that you get like coupling. So, and there's this thing called the the Jordan canonical form, where that's all made. You try to fix things up as best you can, but basically it's a mess. Okay, I'm not a big believer in it. Okay, so to me, eigenvalues are most interesting when the matrix is symmetric. If the matrix is not symmetric and you have SVD decomposition, now you can still do the SVD. The SVD always works, and it still has all these nice properties that the eigenvalue has. This thing is diagonal. Okay, the V's, V and U are orthonormal. So let's, for this case, just for simplicity, let's assume that A is square. So it's n by n, okay? But not symmetric. It's square but not symmetric. So, and of course, if A is symmetric, then the singular value decomposition and eigenvalue decomposition correspond to the same thing, okay? And then A can be diagonalized here by taking U transpose AV is equal to sigma. Okay. So, and the beauty of this is that, well, okay, yeah. So the SVD is very, very handy. Now, okay, so that's just a little background on the SVD. Okay, now, the problem is that we wanted to be able to compute. Oh, hold on. We want to be able to compute. Okay. Now, okay. So let me just go back and review real fast. Okay. So X here. This X here is the is now a matrix, and the matrix is P by N. Okay, so each column of the matrix is an image. You say, well, hold on, an image is 2D. How can it be a column? Oh, well, remember, you always just take the image and you put it in some kind of ordering. It typically would be raster order. So you use raster order to make it into a column. And the reason, the way I like to think of that is that vectors are data. Matrices are operators. An operator is like a function, right? I mean, so a function or an operator takes in data and spits out data, okay? So an operator is like a computer or it's a machine that takes an input, has an output, okay? Is an image an operator? Well, I mean, gosh, I mean, you can do anything, but it's kind of a little strange, okay? I mean, normally, no. An image is data. It's an input to some operation. It's not the operation itself. So an image is best, in my opinion, not thought of as a matrix. You'll never hear me refer to an image as a matrix. It's a 2D array, okay? Because a matrix in mathematics is an operator. It takes an input and it produces an output. In fact, matrices are the canonical way of representing any linear finite dimensional function. Okay, if you have any function which is a mapping from a finite dimensional space to a finite dimensional space, RP to Rn, it can be represented without loss of generality by matrix. It's the most general linear transform from one linear space to another linear space. Okay. So matrices are a representation of operators. So an image is not a matrix because an image is not an operator. An image is data. So So usually when you're thinking about it mathematically, the first thing you want to think about having done with the image is turning into a vector. And usually a column vector, because column vectors are usually data, okay? So each column of this matrix is a column vector, but then we have a bunch of images, because we're going to use more than one image to train the algorithm. So we have n images. So typically this matrix is tall and thin, because there are a lot of pixels, but only a relatively small number of images. So you might have 20 images. Each image maybe has, 100,000 pixels in it, or 1,000,000 pixels in But it's in general, the number of images you have is usually a lot smaller than the number of pixels, right? So you have a tall, thin matrix. Now you want to calculate the covariance in the image. So what is the covariance? The covariance is let me just I already explained this once, but I'm going to explain it again because it's always good to think about these things in more than one way, okay? So the covariance, if I look at R of Ij, what does that mean? Now the first thing that's very confusing to people is because since I've turned the image into a vector, I and j represent the index of pixels. So pixels seems strange to index them by I and j, okay? But think of it, this is the matrix R, okay? And I is this way. So this is the ith row and the jth column. So I here represents some pixel in the image because I put the pixels in raster order. So that entry there is Rij, right? So Rij is the correlation between the ith and the jth pixels. So really, you can think of there's two images here. Okay? So if I take the image, this is, say, the ith pixel in raster order, and this is the jth pixel in raster order, then Rij, that's equal to the expected value of xi times xj, where I and j index the pixels in raster order. So, now I'm assuming this is zero mean, which means you have to have taken the mean off first. So the first thing to observe here is that this matrix is huge, okay? Because let's say that we had a million, let's say we had, even a cheap camera today is a megapixel, right? So a megapixel means that there's roughly 1,000,000 pixels, right? So this matrix here is 1,000,000 by 1,000,000. This is a huge matrix. All the pixels in the image are, there's going to be some correlation, but the correlation tends to drop off with distance. So, but the diagonal, by the way, of this matrix is the variance of each pixel. Now, if the images are assumed to be stationary, then this matrix will have some structure to it, and in particular, it's what's called toplets, or block toplets. I don't want to go into that, but my point here is mainly just that intuitively, the R sub ij is the correlation between pixel I and pixel j. Now, how do you actually calculate the correlation between pixel I and pixel j? Well, what you really do is you do this, okay? You take, let's say x, I'm running out of letters, okay? X n, okay, j, this is the jth pixel in nth image. I know that's a lot to keep straight, okay? So n indexes the image, and j indexes the pixel. Okay, so then if you take x and j, and you multiply that by x n I, this is the ith pixel in the, oops, I better use a different letter. Oh no, in the nth image, right? Now what you do is you sum this from n equals 1 to n, and you divide by n. So this thing then is what we call the sample covariance. Now I'm assuming everything's zero mean here. I've subtracted the mean off first. So when I compute the sample covariance, I take examples of the things, I multiply them together, and I compute the average correlation. This is the average correlation between the ith and the jth pixel. And what I've averaged it over is all the images. So I might have like 100 images. I have image 1, I have image 2, I have image 3. For each image, I compute the correlation between the ijth pixel, and I average over all the images, okay? So this is the sample covariance. Now, the actual covariance, is the image a random process? No. I even won't wait for the answer now, because I believe that you'll answer it correctly. So they're actually, what I told you at the beginning of the class was not true. I said that the Bayesian probability on answers to questions was 0 and 1, but you have to sure add yes and no in there too, okay? There's a pretty high, and I would say they're 50-50, roughly speaking, okay? So if you want to guess at an answer, you can just guess yes or no. That's pretty much binary. But anyway, R here, okay, so does the image a random process? No. Does it really have a correlation? No, because it's not a random process. But we're going to model it as a random process. So we're going to model it as having a correlation. And a reasonable model would be then to say, oh, well, if it really were a random process, then if I computed this sample correlation would be a random variable. Because the x's are random variables. If the image were a random process, these would be random variables, and then this would be a random variable because it's a function of random variable. And in that case, the expected value of S is equal to R. I mean, that's true by the law of large numbers. Assuming that the images are independent, I compute a variable, I compute n versions of the same random variable, I average them. By the law of large numbers, that average will converge to its mean. And that's exactly the definition of the autocorrelation. Okay, so, fine. So that's the sample covariance. So this is my estimate of the true covariance. Now, one of the things that's very interesting is that if I take this matrix X, I'll write it again. So this is going to be x1 through xn. So each column of this matrix is an image, right? In raster order, and I have n of these images, right? This is correct. This equation is correct. But there's an easier way of writing this down. And the easier way of writing this down is this. I take this matrix X, I multiply by X transpose, and I divide by n, and that's equal to S. That is perhaps not very obvious. And I'm not going to try to convince you it's true right now, but I'll let you go off and just play around with it and convince yourself it's true. It is true. There's lots of different ways to think about it. Basically, you're taking the outer product between, when you take the transpose here, this whole thing will flip like this, right? So what will end up happening is that you'll get the outer product between x1 and itself, x2 and itself, all added together. So it's going to really come out the same as this. So these will calculate the same thing, but this is a nice form to it, which makes it easy to manipulate mathematically. So this is the sample covariance. All right. Now, that sample covariance, okay, so now what we would like to do is we'd like to compute the eigen decomposition of the sample covariance. Why would we like to do that? Because, well, we don't know the true covariance R, but we'd like to compute this, we would like to have the eigen decomposition of the true covariance because we've done all this analysis, right? And if we know the eigen decomposition, then we can decorrelate the data in X, okay? It's easier to make decisions about data, and you did that in the lab. But you don't have R, you have S. By the way, one of the most, signal processing is all about making do with what you have, okay? Okay, it's like being a good signal processor is like being a good cook. You have to work with the ingredients you have available, okay? And I'm going to really press this bad analogy to its limit, is that if you're a good cook, you taste it along the way to make sure it tastes good, okay? And if you're a good signal processor, you don't just grind away at all the equations. As you're doing the different equations, you kind of look at it and you see, does it taste good, right? And a really good signal processor will make a tasty a delight at the end, okay? A not so good signal processor won't quite get the flavor, okay? But in any case, okay, so it's all about making do with what you have. And you don't have R, you have S. But you're going to work with S as best you can. So you're going to do the eigen decomposition of S instead of R, and then you'll use that as your basis set. Okay. Now this is where the tricky thing comes in with the singular value decomposition. Well, first of all, the matrix, let me just review. This matrix R is huge. So you don't really ever want to have to compute it. You could compute it in principle, but you don't. See, in math, in signal processing, you often write equations down without ever having the intention of actually evaluating them. They're equations that exist in concept because they help you understand the problem. But you don't actually do it that way. You just use that as a concept to derive something that you can actually do later, right? So this matrix S is much too big to actually use. You need to somehow find a clever way of doing something with a smaller matrix. Now the matrix that isn't too big is X. X is not so bad because X is tall and thin. It's just 100 images or 50 images or 10 images. The problem is that this matrix is 1,000,000 by 1,000,000. This matrix is 1,000,000 by 20, okay? So this is way too big to deal with, but this isn't. So can you do something with X? And that's where the idea of singular value decomposition comes in, okay? So what you do is this. You say, okay, I'm going to take X, and I'll decompose it with singular value decomposition like this. I'll find this matrix U, I'll find a diagonal matrix, and then I'll find this matrix V transpose. Now, I haven't said how to do the singular value decomposition yet, but one way to do it is mindlessly plug it into MATLAB and ask for the SVD, and then it'll return the answer, okay? Okay? Which, practically speaking works, but hold on to that thought for a moment because I'll talk to give you a little more insight into it. But, okay, so X then is going to be equal to U sigma V transpose. Once we have X, then remember S here is equal to X transpose divided by N. So I can divide this by N, and then this is equal to S, and then all this is equal to this divided by N. So X is equal to U sigma V transpose, and X transpose is V sigma U transpose. The V transpose V cancels out, and then I get sigma times sigma, so I just get sigma squared. Because, by the way, sigma transpose is what? What's sigma transpose equal to? So here, sigma transpose equals y. Sigma, why? Because it's diagonal. Okay, thanks. Gee, you guys really are awake. Okay, good. Okay, I'm very impressed. Okay, so sigma there is sigma squared, right? And then, so this is U sigma squared U transpose. So, and there's a 1 over n here. That's a detail. Okay? So this becomes a 1 over n. So the eigenvalues of this matrix S are just the singular values of x squared and divided by n. And U are the eigenimages. Now U is a tall, thin matrix. Tall, thin, okay? So the columns of U normalized are the eigenimages. Okay, now, okay, so now, yeah, basically we're done then, because E is the U is the eigendecomposition, and sigma, well, or squared are the eigenvalues. Now there is kind of an issue, which is like, how do I compute the singular value decomposition for this? Isn't it just as hard as doing the eigendecomposition was? No, it's not. And the reason is that what you can do is this. It's a very clever little trick. And I'll explain it to you, because understanding it gives you, I think, insight into the problem. Which is, the first what you do is this. You can form X transpose X. Now, X transpose X is an autocorrelation matrix, but it has a different interpretation. Instead of it being the sample correlation between different pixels, it's the sample correlation between different images, okay, in your set. So because it's X transpose X divided by, did I divide by the wrong number here? Oh, no, divided by P. Divided by P, okay? Right? This is a matrix, right? And the indices into the matrix are the image indices. So this is of dimension n. And this is of dimension n. So if you have 100 images, this is 100 images by 100 images. And if I look at the ijth entry of this matrix, I'm looking at the correlation between the ith image and the jth image. Now, so this is a small matrix. I mean, this is like 100 by 100, so that's no problem. Now, if I can do, for a 100 by 100 image, I can do eigendecomposition. It's not so bad. If it's eigendecomposition, matrix inversion and eigendecomposition are order n cubed, I think, roughly speaking. So matrix vector multiplication is order n squared, and where n is the dimension of the matrix. And so this is n cubed. So n cubed is bad, right? Because if it's not exponential complexity, but it grows fast, right? So you lose that game quickly. So you don't want this thing to be too big. But that's generally not so bad, because the number of images you have isn't so huge. So this matrix is much smaller than the other matrix. The other matrix is this matrix here. Oh, it's this matrix here. The other matrix is the matrix which is P by P. Right? And this matrix is S is equal to X X transpose. So this is large. Okay, but this matrix here is not nearly as large. So you do singular value decomposition of this, but remember, X here is going to be equal to U sigma V transpose. So X transpose X is equal to V sigma U transpose U sigma V transpose, right? So this cancels, that's I, right? So this is equal to V sigma squared V transpose. So, so this thing here then is lambda. The Eigen decomposition. So if we have lambda here, from lambda we have that x then, x is u sigma v transpose. So if we take x and we, okay, let me redo this. Okay, if we take x and we multiply it by v, that's equal to u sigma v transpose v, but this is I, right? So then we have that x times v times sigma inverse, and we can take the inverse of sigma, assuming none of the singular values are 0, is equal to u. So basically, once we have x, so the algorithm is this. Okay, step 1, compute Eigen decomp of x transpose x. So you get x transpose x equals v lambda v transpose, okay? Step 2, use x and v to compute u and sigma. So how do you do that? Well, first you get that u equals x v v times sigma inverse, and that's equal to u. Now you say, well, what's sigma inverse? Well, you know that the columns of u must be normal. So sigma inverse, where sigma is equal to, you take the diagonal of xv transpose xv. Square root. In other words, all these sigma does is it takes the columns of this matrix, x times v, and it normalizes them to be, it makes them normal, because u has to be normal. If you don't multiply by the sigma, you'll get the unnormalized version of u. So the idea here is that you can actually solve the problem. You can find the eigenimages, which are this big matrix, by really only solving a problem which is on the order of the number of images you have rather than the number of pixels. So that's a key innovation that reduces the complexity a lot. So this is the fast eigenimage algorithm. Okay, it's a kind of very clever thing. Okay? And then you did the lab and you applied those. It would have been good if I had come in with some images. But you did the lab, so you saw how then the bases, these bases U could be then used to describe images and do, for various applications like classification. So eigenimage analysis and eigensignal analysis is very useful for a variety of applications. One of the things it's used most widely for is just dimensionality reduction. So if you have an image, there's a lot of pixels. So by taking the first 10 or 100 eigenvalues, you reduce the dimensionality of the object a lot, so it's easier to deal with. So you can think of it as compression. The other thing it's used for is to decorrelate. It decorrelates. It gives you decorrelated variables. Decorrelated variables are very important because then they represent different underlying behaviors that are essentially orthogonal to each other. Right. So, and this is related to a lot of other things like Fisher linear discriminants that, if you get into this sort of stuff, are pretty widely used. Okay? Are there any questions about this? I know this is a fairly abstract part of the course. Okay? Good. All right. So now we're going to go on to the next topic. The next topic is, we're going to get into edge analysis. Okay, so I think we're going to try to go through this stuff fast. Neighborhoods. We have neighborhood behaviors and images are very important. People commonly talk about using 4-point neighborhood and a 2D lattice, or 8-point neighborhood. So in an 8-point neighborhood, you include the 4 corner points. I think there's nothing really deep there. Boundary conditions. I know that people often get upset about boundary conditions because when they go to process their image, they're not sure what to do when they get to the boundary. Part of the answer is it doesn't really matter that much, okay, practically speaking. But not always. Sometimes it does. But, but there are a few standard things people do. One thing is that they do is you can use a free boundary condition where you just you pretend the values outside of the image are 0. You can use a toroidal boundary condition, or you can use a reflective boundary condition. So if you have an image, okay, so the question, you're here, right? And you go to reach out to get a pixel here, okay? The problem is there's nothing there. By the way, if you try to read that data in the program and you haven't put like in some conditional statements or done something, guess what's going to happen? If you're lucky, you'll get a segmentation fault. If you're not lucky, it'll run just fine, okay? Why is it better to get the segmentation fault? Because then you know you have a bug, okay? So it's important in your programming to be a pessimist, okay? And to be hoping that something will go wrong, okay? Now, so if you've got a toroidal boundary condition, it's like you're in some sort of parallel universe, and you pop out the other side of the universe and come over here, okay? Yeah. And then the other possibility is that you reflect back in. Actually, this is one of my favorite parts of the class because I get to talk about one of the things I really like in life, which is when I was an undergraduate, I spent a lot of time playing this game. I wasn't ever very good at it. It's called Asteroids. They had one in the bar I used to like to go to. And so you have these these asteroid things. Has anybody ever played this? Okay. And sometimes there's like a gravitational force field that pulls you in. But when you go flying around, sometimes you get up a lot of momentum. And you'll go flying over here. Do you know this was supposed to be the first? I have it on fairly good authority. This was the first video game. Now, maybe Wikipedia will disagree with me. Wikipedia knows more than I do about this, I'm sure. And the reason is, if you notice that when you draw these figures, and they're like these things are like line drawings, right? The original like graphic displays weren't raster like what we have on these displays. They were actually they drew with like lines on a phosphorus display. There were these Tektronix, like the people who makes the oscilloscopes. They made oscilloscope's a little bit like a display. So you can imagine it was like an oscilloscope, only it was for displaying. And you'd actually draw on the surface with this thing. There was a thing called a 4014, I think it was, these were really expensive, okay? When I worked at Lincoln Lab, and we have one person in the audience who's actually attending this course from Lincoln Lab. Hi, Paul, right? I think your name is? Okay. The Tektronix scopes, we had these Tektronix displays. It was really cool. And these were how you displayed things. So, of course, the first thing people ever do when they have a new technology is to try to make a game out of it, okay? So they tried to make video games, okay, on these scopes. And so the only thing they could do is draw stuff like this. So hence you have asteroids, okay? So asteroids, so this guy would go flying, and sometimes you'd get up a lot of speed, and you'd come back over here, and then you'd fly and you'd hit this thing here without seeing it coming. Oops. Right, so that's a toroidal boundary condition. And the way you can think about that is that if this is a piece of paper, you're doing this, right? You're attaching the two ends like that. But now, if the paper were flexible, you'd get it into a tube like this. And you'd take the two ends and you'd bend it around like that and you'd connect it on the other end, right? It's not quite flexible enough. And that's called a toroid. It used to be a Taurus was a car made by Ford. But in fact, it's a donut shape. See, I'm not very good at drawing a Taurus, but it looks something like this. Okay? The other possibility is, of course, reflective. Now, toroidal boundary conditions are actually important from a theoretical point of view because that's like a ring. So you can, like FFTs, actually operate on a toroidal structure. So you can get exact solutions to some important theoretical problems by using a toroidal assumption. Often it's not practically very meaningful because it's often not the case that it would be reasonable to assume that the right-hand side of the image is connected to the left. Although there are some exceptions. There's some applications in like halftoning we'll talk about later where you have a screen and the screen has a periodic structure, so it's a perfect toroid. Okay, now, edge detection. Okay, I've talked about this already. So edges are very important in images because they contain a lot of information. You can take an image and just detect edges in it, and you can really get a lot of the visual content, right? Or, in cartoons, you often just draw edges, and you can really, visually get most of the information. The problem with edge detection as a problem is, well, there's all kinds of problems with edge detection. One is that there's no universally accepted definition of what is and what is not an edge, okay? It really depends upon your application. So it's an ill-posed problem in that sense. Also, even if you have a perfect definition of an edge, so there's some oracle that can tell you this is an edge and this is not an edge, that, detecting it with certainty is generally not possible, right? So as with any problem you have where you have to detect something, you're going to have a trade-off between the probability of false alarm and the probability of detection, okay? So usually you can do something like this. You say, oh, this is the probability of detection. So this is 1, and this is 0, right? And this is the probability of false alarm. This is 0, and this is 1. This is the probability of false alarm. So probability of false alarm is the probability that the edge was not there, but you detected it erroneously, okay? And the probability of misdetection is the probability that the edge was there and you didn't detect it, right? So I can always have a perfect probability of detection. It's quite easy. So in order to have perfect probability of detection, I just declare everything as the detection, okay? So it's like, I just say, it's there, okay? Independent of any information, right? So here, I can always be there, okay? That's easy. Now, I can also have a perfect, I can always ensure that I'll never have a false alarm, okay? So all I have to do is never declare anything ever there, right? So that point is also there. Now, in practice, having a high false alarm rate is annoying to people, right? Because if you have a system in your car and it says, warning, warning, and warning, warning, what are you going to do? You'll turn it off, okay? Okay. Any self-respecting engineer would do that, right? So the trick is to have a high probability of detection with a low probability of false alarm, okay? So the curve you get here, is typically something like this, okay? And it should always be convex because you could always do the following. You could take 2 points on this curve, and you could randomize so let's say some algorithm produces this probability of detection false alarm trade-off, and this one produces a different point of trade-off, okay? Well, you can randomize between the choices of those 2 algorithms, and you'll get a straight line connecting them. So you should always be able to do at least as well as a straight line connecting the 2 dots. And that's the definition of convexity. So this function here is, so let's say this function is f of lambda is equal to the probability of detection given that lambda equals the probability of false alarm, okay? So that's the function. The function is said to be convex, or technically speaking, this is concave. Concave. If f of, I should have used a different letter here. Can I change that to an A? Thank you. Okay, so if I take f of A times lambda plus 1 minus lambda times f of B, okay, and then I can take f of lambda A plus 1 minus lambda B, okay? So this is A, and this is B. And this is f of A, and this is f of B, right? Now this is some combination lambda, f of A and B. So this thing has always got to be greater than or equal to that. I think I got that right. Yeah. So this is called concave. A function is concave if it has this property. If the inequality goes in the other direction, it's called convex. Now, so this curve here is called the receiver operating curve, or ROC. Every community that's ever tried to solve a problem like this has either independently, usually they independently rediscover this, okay, or they refer back to this, okay. But I think the communications community was the first one to really quantify this concept. So everybody calls it an ROC curve, unless you're like in a medical school, because doctors never listen to anybody else. So, excuse me?
What is lambda?
Oh, lambda? Oh, lambda is any value between 0 and 1. So it's, in other words, you're taking a convex combination of the A and B. That puts you at some point in between. So the value of the function, let me just draw this a little bit more carefully because it's not zoomed in enough. So let's say that's a concave function, right? So this is A, right? This is B, right? So this goes here. So this point here, this is f of B. This is f of A. This is a little more zoomed in. This is lambda A plus 1 minus lambda B. So it's somewhere in between. And then this point here, that is f of lambda A plus 1 minus lambda B, right? And now if I draw this like that, that's supposed to intersect at that point. Then this point here, that point is lambda times f of A plus 1 minus lambda times f of B. Oh, I'm running out of time. Okay, so that point actually falls below. So that's an illustration. Okay. All right, good. So this is a receiver operating curve. And that's the basic trade-off we have in edge detection. So, okay, see you next time. Bye.